Could you put your hands up if you've used know of JSON? Okay, pretty universal. Okay, for those of you that haven't, and it's JavaScript object notation. It's basically a JavaScript-based data format. If you've used tools like MongoDB or something, then that works on over JSON documents. It's very, I find it a very kind of powerful and intuitive way of expressing data. But again, it doesn't have native links. There's not a JSON data type, and not a data type within the JSON specification that defines that something is a link. So again, if you're writing an application that processes some JSON data, then and you know which things are links to other resources, then you have to encode in your application a mechanism for identifying links based on the structure of the string, and then deciding whether to follow them or not. There's some scope for context information in JSON. There's JSON LD, which I'll talk about a little bit later on, which enables you to embed some more contextual data about the meaning of the keys that are used in the JSON document. But again, it's unclear. It's not particularly apparent how powerful or how well used or well supported that additional schema information is. There's also JSON schema, which is kind of analogous to XML schema, but again, it doesn't have a data type for a URI. So there's a point that I'm getting to about. Okay, I'll save that for later. So XML is in a similar position to JSON in that it does have some kind of notion of native links. In that there's the XML schema data type, any URI, which you can use to say that the values of this element. If I have an XML document and this XML schema, then the schema can say, well, the value of that element should be a URI. So you can use it from kind of validation purposes. But it's not really clear inherently in the data model that is a link that therefore should be followed. And similarly, the schema information provides a way of expressing some kind of context that's not particularly rich. It doesn't provide you with a mechanism for expressing the provenance of the data, like we discussed before, and it doesn't provide you with a way of kind of providing additional metadata that gives some kind of guarantees or claims about the veracity of that. So to think about all of these data formats, like data formats without native links are really like having the HTML markup language without the anchor tag. So imagine writing a web page where you wanted to include some links, but you didn't have an anchor tag to use. You'd be faced with literally including the string of the link, but with no way to indicate to a browser that is a link, that's something that should be followed, which in a web context is absolutely crazy. So there has to be some mechanism for conveying to tools in a much more lightweight, easily processed fashion that this is something that should be followed. So yes, you could implement a web browser if HTML didn't have the anchor tag by looking at every string in there and deciding whether to follow it, but it would be a very, very painful process. So by adding that simple tag, then that creates the ability for people or applications to know whether to follow links or not. Unfortunately, these data formats don't particularly do that. Don't do that in any reliable sense. So what we need is a universal data model and corresponding formats for the web as a whole. So what are the requirements of this? Well, we need to be able to model tabular, tree-like, and key value data with this format. So we need to be able to handle all the typical kind of structures or general data shapes that XML, JSON, CSV provide. We need links to be a first-class citizen of these data formats. So it's not enough to say, yes, I can include in my data format string that starts with HTTP. We need some mechanism for conveying to applications consuming that's a link that should be followed. We need some extensibility mechanism, which was raised earlier on, where we can provide rich context around this data. So we're limited to just providing the column names in the header. We actually need to provide some mechanism for saying, this is the data, this was when it was created, this is when it was published, this is who created it, this is who published it, This is the collection protocol that was used. These are the instruments that were used in collecting this data. These are the known assumptions or errors that exist in the data, etc., etc., etc. We need some way for that data, when it's moved around, to be able to be traceable back to the original source and verified. So what we found is that modeling everything as a graph is a very powerful way of describing data, particularly as a directed graph. So we can say Tom is affiliated as an affiliation ODI, and when you start looking at the world in this way, then you find it's a very, very compelling way of looking at the world, and almost becomes infectious. You can't stop thinking of the world as a graph. And it's almost everything can be modeled in this way, and there's some exceptions which I'll talk about later, which are more complicated. So does this, if we approach everything as a graph, does this enable us to model the tabular data that we might see in a CSV file? So if we imagine a fake data set about the speakers at the summer school, we can say, yes, Tom has affiliation ODI. So we can treat the property here as in the middle as a column name, and then each of the attributes as cell values. So if we take a JSON example, can we model something that we typically model in JSON? Can we model that as a graph as well? The answer is yes. We can have a key with a value Tom, and then affiliation ODI. Works pretty easily. Similarly with an XML document, we have, yes, there's a speaker named Tom, affiliation ODI. Very simple. All of the stuff that we typically model using these other formats, we can model as a graph. So we've fulfilled the first of our requirements, the ability to model these different forms. So what about links as a first-class citizen? So taking the CSV example at the top, is that link in the second column, first proper row of the second column, is that a first-class citizen as a link? We can see that it's a link, or we assume that it's a link, but does the data format represent that as a link? The answer is no, for all the reasons I've explained so far. The same with the JSON example. Yes, we as human beings, or someone if you wrote a regular expression, you could say, yes, that's probably a link. It doesn't have spaces in it, starts http://. So we could treat it as a link, but there's nothing inherent in the format that says this is a link to be followed. Same with the XML example. So as a browser or some application consuming that, then what are these applications supposed to do with this data? It's really not clear. So enter RDF. The Resource Description Framework is a universal data model for the web. So based on the notion of a directed graph, it's a W3C standard, has been for many years, and is the underpinning of the semantic web. It's the key component of the semantic web technology stack. Its relationship with semantic search is, so you can have semantic search that isn't based on RDF, but there's an increasing amount of data on the web which is either published in RDF or is easily converted into RDF. So let's think about the basics. So data is simply modeled as in a graph as connections between things. So it's simply a directed graph, and a graph as a whole consists of one or more RDF triples. So a triple is a three-tuple of the subject, predicate, object, pretty much like natural language. So Tom, affiliation, ODI. But you might look at that and say, well, okay, where's the webbiness in that? It's just a graph. None of the elements actually mean anything. What RDF actually provides us is a mechanism for grounding each of these things that we're describing in the data in the web. And the way that we do that is through using URIs. So historically, we've all grown up with the notion that URIs are identifiers for web pages. You put a URI into your web browser, and you get taken to a web page. URIs actually are identifiers for anything. So I think the original proposal for the name was that the acronym should stand for Universal Resource Identifier. Actually, I think Tim Berners-Lee describes in his book Weaving the Web about how some political debates within the standardization committee actually actually kind of reduce the universality of this, kind of reduce the claims that are inherent in the term URI. So now it's what universal resource identifier, or uniform resource identifier rather than universal. But the reality is you can use a URI to identify anything. So here we've got a URI for me, top there. You can look that up. It works. And then URI for my home page. And then you've actually got a URI here for that represents that relationship of home page, the relationship between the person, me, and the document, my home page. So it can get a little bit complicated or verbose to look at these with these fully qualified URIs. In fact, I've left off the HTTP there, which is an error. Apologies for that. So we can actually abbreviate these in some way. This is the kind of informal notation I'm using, but we can start to abbreviate them with common prefixes. So this both vocabulary stands for friend of a friend, and it's basically a vocabulary that's been in use for many years for describing people and interesting aspects of people. So email accounts, social media accounts, places that they work, home pages, pictures, that sort of thing. The kind of stuff you'd expect to see in the profile of a social networking site. So RDF makes a distinction between resources and literals, and this is where we get into the ability to distinguish between things that should be followed and just plain strings. So I can create a small graph of two triples that says there's this thing identified by tomheath.com/id/me. It has a particular home page, which is a resource. And again, I'm using a kind of informal notation here, where the angle brackets identify a resource, and literals are just simply in quotes here. So there are many, many ways to serialize RDF. And I'm going to talk a little bit about them because they all have different use cases and different strengths. So in triples, it's kind of, it might be hard to get a sense of this because it's squashed onto one slide, but in triples, each triple is fully qualified with a fully qualified URI if it's a resource, and terminated by a full stop at the end. So you can imagine in a scenario with a wider screen where each triple ends up on one line. So this is a great format this is the simplest format around. It's in a way it's very easy to read because you have one triple per line, subject, predicate, and object. The relationship between them is very clear. And it's also very good for processing. It's highly compressible. All the redundancy in the URIs means that it's highly compressible. So it's great for shipping data around. And it also means that because each triple typically occurs one per line, then you can when you're processing this data, you can stream through it very fast. Or you can stream through it without having to load it into memory, which is not the case with things like RDF XML, which I'll talk about in a minute. So you've got a very big data set that you need to stream through, then N-triples is by far the best way of doing it. There are some issues when if you want to process this in something like MapReduce, because you can see a scenario here where actually there's triples about me on different lines. Each one of these lines each one of these triples has the same subject, this, and so if I want to do something that like a MapReduce job in Hadoop that looks at properties of me and uses this as the key, and then extracts some other properties or does some processing over the combination of multiple properties, I've first got to write a MapReduce job that combines all of the predicates about me into the value with the subject URI as my key. I don't know if this is making any sense, but just if it's not, then know that if you come to process RDF with Hadoop and MapReduce at a later date, this is the kind of issue that you'll have. N-triples is the best place to start, but it's not without some complications. So N-triples is a subset of Turtle, which is a format that's a serialization which has recently been standardized by the W3C. It's great in that it's very human readable. Its main selling point is that it's human readable and easily human writable. So you can see here there's the same three triples. The subject here of all of them is this, and then these are the predicates, and these are the objects. So again, it's using the same kind of notation that I was using before, where literals are in in quotes. Resources are in, things which should be followed are in angle brackets. And it's just, Turtle basically introduces some abbreviation mechanisms to make the data less verbose, make it more readable. A key part of that is introducing this notion of prefixes, so you don't have to fully qualify the names of each of the predicates or any of the URIs, any of the resources in the data. And to go back to my favorite issue of how to process this stuff in MapReduce, what you can actually do if you have control over how the data is written is you can actually use Turtle to write the data where all of this, where there are no prefixes used and all of this is compressed onto one line. That's valid Turtle. You can remove the line breaks and keep these delimiters here, the semicolon and the full stop, and put it all onto one line. No one really seems to talk about this as being a way forward. Maybe everyone just does it automatically without thinking about it. So RDFA, which was raised earlier on in the context of ERDF and mechanisms for embedding RDF data within HTML pages. So this can really be seen as the natural successor of things like microformats. And I think the microformats community would hate me for saying this because there's traditionally been friction between the semantic web community and the microformats community, but this is like microformats done right. God, I'm really digging a hole for myself here. This is being videoed, isn't it? So you can see when you look at it that it's more complex to look at. You're basically taking the HTML DOM, and what RDF defines is a bunch of additional properties that you can, additional attributes that you can introduce into your HTML DOM that encode the data, that it effectively is RDF data, serialized in a particular way. So there's the about attribute, type of, rel, and property here. Actually, that's fine. So this distinguishes between literals and resources. And type of gives an indication of the class of the information, of the class of the thing that's being described, which is identified by the about statement here. So there's big claims made about RDFA being it's much easier to deploy than the other serializations of RDF because you can do it in your HTML documents. So if you want to publish Turtle data, or N triples or RDF XML, on your website you need to publish that alongside the HTML pages. And then you need to introduce some mechanisms for handling what happens when someone looks up a URI like this. So if you look up that URI, then if you do it in your browser, then you'll be redirected to my home page because the script that handles that identifies that you're accessing it with a browser. If you access that with a linked data crawler, that URI, you get redirected to somewhere else, to a different document that encodes somewhat comparable information in an RDF serialization. In my case, RDF XML, because that's kind of the convention, or that's been one of the historical conventions. So if you adopt one of these non-RDFA serializations, you have more work to do in deploying more documents on your website or writing scripts that generate more documents in different formats. The advantage of that is that you don't have to try and get your data into this particular format, which is it's both a pro or a con depending on your publishing scenario. Now if you do this once in a template, you can validate it, you can check that it's right, and that's fine. Trying to write this stuff by hand is hard. Big claims are made about it being kind of hand-writable. It's really hard. So you have to effectively mentally parse the DOM, the HTML DOM yourself, and get a sense of what you're adding to what different bits of the structure. But it's really powerful and it's really popular amongst people that use particular templated content management systems, that sort of stuff. And it's also been most heavily adopted by search engines. As far as I know, of all the different serializations, then the FA is the one that's most heavily adopted because, for one really important reason, that the crawlers in the search engines don't have to build new crawling processes to publish different data formats. They can maintain the same crawling mechanisms for HTML data and they get a load of HTML content and get a load of data for free. So that's my understanding of why RDF has been particularly successful, because it maintains that same infrastructure, or it doesn't require building of new infrastructure. I don't know what crawlers do with this. I don't know whether a Bing crawler or Yahoo or Google would actually look up that URI. Maybe Peter can elaborate tomorrow, reveal some commercially sensitive secrets on camera. We'll see. So last of all, RDF XML. So for many years, RDF XML was the only standardized serialization of RDF, and it was mandated within the RDF spec itself, I think. So for many years, everyone deployed RDF and RDF XML, and it was originally developed as a way of making RDF data accessible by existing HTML tooling, XML tooling. But actually, what it did instead was just confused a load of people, because what you've got here is a graph-based data model being squeezed into something else, and people looked at it expecting to be able to read it in the same way that they'd read XML, and instead they just saw a load of other stuff like all of this RDF resource, and it actually limited people's ability to understand the fundamentals of the RDF model in terms of a graph. And actually the benefits of being able to process it with existing XML tools were rather limited. So it was kind of an attempt with good intentions that, as far as I know, it's still being standardized as part of the RDF2 working group. I don't know if that working group's finished yet, but there's been a lot of debate, a lot of disagreement about the appropriateness of JSON LD, whether it's really an RDF serialization, blah, blah, blah. I haven't gone into detail here because it's still something that's very much in progress, but Gmail have started to introduce this, and what we're seeing is that they introduce support for this, so that if certain people email you with certain data embedded in that, then Gmail will start to do intelligent things with that, like adding stuff to your Google Calendar. I'm sure there are lots of examples from other big web companies doing this sort of thing, but we can see how the kind of structured data that Tim was talking about in his original vision of the web, structured data with predefined formats, can enable more intelligent things to happen, can enable applications to do more interesting things. So in 2006, in this document referenced here, Tim Berners-Lee set out these 4 linked data principles. So if you imagine what was going on at 7 years ago, then we'd had lots of work invested in the semantic web technology stack. So RDF had been around for a number of years. There was RDF schema and OWL, which I'll talk about a little bit in a moment. And there was lots of research papers saying, well, if we had a semantic web, then we could do this, this, and this. And here's my very elaborate paper on some kind of aspects of OWL reasoning, assuming the existence of this semantic web. But it didn't actually exist beyond some very simple kind of fictional examples like the famous wine ontology or pizza ontology, these sorts of things that people had written as training materials and as demonstrators. But there was very, very little real deployment. And what happened was that Tim outlined these principles which helped people really get a sense of what his vision was for how the semantic web should be or how it should be built or deployed. And they're very simple. So the first one is literally use URIs as names for things, i.e. not just your web pages, but as names for, and by names I mean kind of identifiers. So documents, computers, places, people, concepts, times, particular time points or time periods, all sorts of things, anything that you want. Use a URI to name that thing. But crucially, use HTTP URIs so that people can look up those names. So the key thing here is if I create a URI in a different scheme, in a non-HTTP scheme, like the tag scheme or URN or something like that, then there's no There's no widely deployed, globally deployed mechanism for looking that up. I can't put it into a web browser. The web browser doesn't know what to do with it if it doesn't begin with HTTP or HTTPS or FTP. And so all of those sorts of URIs are dependent on some other kind of lookup directory, some kind of central registry that maps between the identifiers and the objects themselves. So if you think about a DOI, a digital object identifier that you might have for a journal article or an ISBN for a book, all of those are assigned by practically, in practical terms, centralized organizations. So there'll be a central authority for each of those, and they'll distribute a portion of those namespaces to different organizations who can process those. But if you want to look up a DOI, then you have to go to some kind of central registry. There's not a global infrastructure for doing this. It's a really subtle thing, but it's really, really important if we're going to actually make this thing scale. So when someone looks up a URI, provide useful information. And Tim later amended these principles to say, provide useful information using the standards, i.e. RDF and Sparkle. But in the case of my URI that I talked about before, when someone looks that up, then in the first case, yes, redirect them to HTML if it's a browser, or provide useful information in RDF if it's a linked data or semantic web application. And in that data, then, the really key thing that makes this a web is including links to other URIs in the data. So all of those data formats that I talked about before, Excel, CSV, JSON, XML, they're dead ends. They're like leaf nodes in a tree. For something consuming that data, there's really nowhere for them to go. They don't have the applications or the tools don't have a clear indication of where to go. They just kind of find the data and stop. What was to be achieved here was encouraging people to actually build a web of their data itself, where each piece of data isn't a dead end. It isn't the point where the application stops. There are links included that can into other related information. So if we go back to my previous example, then I've added an additional triple here using this based near property and using this URI. So, well, I've added two things actually. So there's a thing here that actually has a type, both person. So I've added some type information so that something consuming that can get a sense of what type of thing is being described. And I said it's this thing, which has a name Tom Heath, is based near this thing here. If you go to the very start of my talk, I gave that aerial view of East London, and there was the roundabout, Silicon Roundabout at the bottom. It's actually called Old Street Roundabout. So what I'm saying here is that I'm based near this thing. And this thing here is defined in a different data set. This is defined in DBpedia. And DBpedia is a project that basically takes the dumps from Wikipedia, extracts as much structured data from there as possible, primarily from the info boxes at the right-hand side where you see what are effectively key value pairs, and basically produce an RDF data set that includes identifiers for all the concepts in Wikipedia, and then as much structured data about those things as possible. So what I'm doing here is I'm linking my data, my description of myself, to something else in the broader web. I'm outsourcing my management of location data to DBpedia by saying I'm based near this thing. So if you want to know more about the location where I'm based, you can do it there. You can find it there instead. You can find a latitude and longitude. You can find hopefully other things that are nearby to that. Read more about the type of area, the district that it's in, etc., etc. So to do this, that I have certain levels of trust or a certain confidence in the quality of the data that's provided here. And in this case, it's my personal homepage or my personal RDF description. So I'm happy to trust that DBpedia will continue to exist, that the data that's in Wikipedia is reasonably accurate. And because if that ceases to be the case, then it doesn't really matter. No one's going to die. There's not going to be some big disaster. If I was doing something like a medical application, I might choose to place certain additional constraints on the data sources that I link to because I'd want to have stronger guarantees about how much I trust those. And what you can see here is that we're building up a data structure which starts to be very rich from a query point of view. So this simple thing, this simple fragment of RDF could enable someone to ask the query, tell me all the people, all the 5 persons that are based near Old Street Roundabout. Then you can start to see the beginnings of some interesting applications based on linked data. So you could imagine that I might point to another data set that described startup companies in East London and when they were founded, how much funding they've had, how many people work there, and what their area of business is. So it might be that I'm a recruitment agent looking to recruit a data scientist or a programmer in East London, and I want to go and steal someone from a different company. So I could say, right, find me all the people that work for a startup company in East London that has been funded in a certain period of time and is running out of money and have a specialization in machine learning. So which companies are about to go bust, which I can go and steal some machine learning experts from. So that's the kind of query that we can start to answer when we have an unbounded web of data. So in terms of data modeling, I talked earlier on about this FOAF vocabulary for defining or describing people. That's just one example of a vocabulary that defines a certain domain. So on top of RDF itself, there's RDF schema and OWL. These are both mechanisms for describing things or defining the vocabulary you'd use to describe things. So I could write a vocabulary or an ontology for locations or drinks or